In the architecture of our solar system, there exist worlds where the very concept of weather becomes meaningless. On some planets, storms are impossible. Consider Mercury, that scorched sentinel closest to our sun, a world superheated beyond the tolerance of atmospheric retention. Mercury is too small, its gravitational embrace too feeble, and its proximity to our star too intimate to clutch and hold a significant atmosphere against the relentless solar wind. Without an atmosphere, there can be no exchange of heat, no circulation of gases, no turbulence, no conflict between pressure systems, and so no storms. The surface of Mercury bakes in silence, a dead world of extremes where the sun looms 3 times larger than it appears from Earth, where temperatures soar to 800 degrees Fahrenheit on the daylit hemisphere, hot enough to melt lead and zinc, while the night side, receiving no moderating blanket of air, plummets to nearly 300 degrees below zero. It is a place of stillness, of ancient impact craters frozen in time, of cliffs that stretch for hundreds of miles, testimony to the planet's slow contraction as its molten core cooled over billions of years. But move outward, away from the sun's fierce grip, and the character of the planets transforms. Here, in the zone where starlight weakens and temperatures moderate, we find worlds wrapped in thick, turbulent, chaotic atmospheres. These are realms where gases churn and collide, where temperature gradients spawn circulation patterns of breathtaking complexity, where the physics of fluid dynamics orchestrates performances on a planetary scale. They can spawn some of the most awe-inspiring megastorms in our solar system, phenomena that dwarf anything we experience on Earth. Tempests that rage for decades or centuries, vortices that could swallow our entire world whole. This is Venus, Earth's twin in size, but alien in every other regard, a planet completely shrouded with clouds that stretch in unbroken layers around the entire globe. From space, Venus appears serene, a brilliant pearl reflecting more sunlight than any other object in our night sky save the moon. But this beauty masks violence. High above the hidden surface, winds rip around the upper atmosphere at over 300 miles per hour, velocities that exceed the fastest hurricanes Earth has ever generated. At an altitude of about 35 miles above the surface, far above the crushing layers below, the winds are whipping around in a ferocious pattern that basically carries the cloud features around the entire planet every 4 Earth days. This phenomenon, called superrotation, remains one of the great mysteries of planetary science. The atmosphere itself rotates 60 times faster than the solid planet beneath it, as if the air has somehow decoupled from the world it envelops, spinning independently in a mad carousel driven by forces we still struggle to fully comprehend. Venus is closer to the Sun than Earth, orbiting at a distance of 67 million miles compared to our 93 million, and it is heat from the sun that drives the wind, though not in the way one might expect. The circulation pattern of Venus's clouds is actually quite simple compared to the Baroque complexity we see on Earth. There is a warm side of Venus, the hemisphere facing the sun, and a cold side, the hemisphere turned away into darkness. As air warms up and rises on the day side of Venus, heated by the unrelenting solar radiation pouring down through the thick carbon dioxide atmosphere, it spreads around to the night side where it cools and descends. So there is this continuous current, a planetary scale convection cell that wraps around the globe. It is actually quite a lot simpler than the atmospheric circulation on Earth, where the rotation of the planet, the distribution of oceans and continents, the tilt of the axis, and the variation of seasons create multiple circulation cells, jet streams, and weather fronts of enormous complexity. Venus, by contrast, rotates so slowly that a single day on the planet lasts longer than a Venusian year. This sluggish rotation simplifies the atmospheric dynamics, creating a more straightforward, if more extreme, pattern of circulation. Venus's winds circulate faster than the fastest hurricane on Earth. Yet, when we examine them closely through radar imaging and probe data, they look very similar to the tropical cyclones we know. The Venus Express probe, launched by the European Space Agency and arriving at Venus in 2006, captured these remarkable images of the planet's south pole, and what it revealed left scientists speechless. One of the great mysteries of Venus, which actually had jaws dropping in the halls of many astronomy departments, is the fact that we have hurricanes at the poles of Venus, especially in the southern hemisphere, that have two eyes. Not one eye, but two eyes. Now, we have never seen this before on such a planetary scale. Hurricanes on Earth possess a single central eye, a region of relative calm around which the storm rotates. But Venus's double-eyed vortex measures 1,800 miles wide, an atmospheric monster where two hurricanes whirl around each other in an intricate gravitational dance, their spiral arms intertwining like cosmic serpents. The formation mechanism remains hotly debated. Some scientists believe it results from the convergence of atmospheric flows at the pole, where the global circulation pattern forces air downward, creating a standing wave structure. Others suggest that instabilities in the vortex itself cause it to split or oscillate between single and double configurations. If you could descend into the vortex of Venus, something I would love to do, at least with a remote machine, I think you would see some kind of a fantastic wall of cloud, towering structures of sulfuric acid droplets rising miles into the sulfur-tinted sky, and this sort of twisting form spinning around you at ferocious speeds. It would be quite a sight, though it would also be your last if you were unprotected. The clouds themselves are not water vapor as they are on Earth, but concentrated sulfuric acid, a corrosive substance that would dissolve metal and organic material alike. These acid clouds form at altitudes where the temperature and pressure allow sulfur dioxide to combine with water vapor, creating droplets that fall and then evaporate before reaching the lower atmosphere, only to be recycled upward again in an endless caustic rain that never reaches the ground. It is a mystery how deep this raging, spinning vortex goes, whether it extends down through the cloud layers into the clearer atmosphere below, or whether it is confined to the upper reaches where the winds are fastest. But maybe this megastorm eye descends all the way to the planet's surface, a vertical tunnel of circulation connecting the stratospheric hurricane to the scorched landscape far below. Down here at the bottom of this crushing ocean of gas, permanent twilight bathes a volcanic landscape in orange and brown hues. The thick atmosphere scatters light so efficiently that even at noon the sun is invisible, diffused into a generalized glow that seems to come from everywhere and nowhere. And the atmosphere's colossal weight creates immense pressure at the surface. The atmospheric pressure on Venus is about 100 times that of the Earth, equivalent to the pressure you would experience if you dove nearly a mile beneath the ocean's surface on our world. Think of taking a car, an entire automobile weighing several thousand pounds, squeezing it down to about a square inch, and putting that weight on every square inch of your skin. You would be flattened within a fraction of a second because of all that pressure, crushed like an aluminum can in a hydraulic press before you could even register the sensation. Venus's dense atmosphere creates one of the strangest megastorms imaginable. 4-mile-per-hour winds with the force of a hurricane. This seems contradictory, almost impossible, yet it is the reality of this alien world. The winds on the surface of Venus are actually very slow because Venus has a very slow rotation rate. It takes Venus about 8 months to turn once around with respect to the Sun, meaning that from any point on the surface, the Sun appears to creep across the sky at an agonizingly gradual pace, taking nearly 60 Earth days to travel from horizon to horizon. This leisurely rotation would normally produce gentle breezes, barely enough to rustle a flag if one could survive there to plant it. But the crushing atmospheric pressure rams gas molecules together so tightly that they feel more like a liquid than a gas. At the surface, the atmosphere is so dense that it behaves almost like a fluid ocean, and moving through it would be like wading through water. A gentle 4-mile-per-hour breeze, which on Earth would barely be felt on your face, packs a brutal punch in this environment. It is like a hurricane in slow motion, exerting forces comparable to much faster winds in Earth's thin air. Winds on Venus are totally unlike anything we see on planet Earth. You would almost feel like a molasses effect, as if the air itself had weight and substance beyond anything we experience. It would be quite difficult to simply walk and run through the wind, even though the wind speed itself is modest by terrestrial standards. The density changes everything. Each step would require pushing against a wall of compressed gas, and any structure built on the surface would need to be engineered not just to withstand high temperatures and corrosive chemistry, but also to resist the lateral forces exerted by this dense, slow-moving atmosphere. NASA's early Venera landers, built by the Soviet Union, were designed like bathyspheres with thick titanium pressure hulls, and even they survived less than 2 hours on the surface before succumbing to the combined assault of heat, pressure, and chemical corrosion. Venus's surface is so hostile that life, at least as we know it, is impossible here. No organic molecule could withstand temperatures of 900 degrees Fahrenheit. No liquid water can exist where the pressure and heat would turn it instantly to supercritical vapor. The rocks themselves glow dull red in some regions, not from volcanic activity necessarily, but simply from the ambient heat. It is a vision of hell made real, a cautionary tale of what happens when a greenhouse effect runs away unchecked, when carbon dioxide accumulates in an atmosphere and traps heat with such efficiency that a planet transforms from a potentially habitable world into a pressure cooker. Early Venus might have had oceans, a temperate climate, perhaps even the conditions necessary for life to begin. But as the sun gradually brightened over hundreds of millions of years, as it has and will continue to do throughout its life cycle, those oceans evaporated. Water vapor, a potent greenhouse gas, amplified the warming. Eventually, the hydrogen escaped to space, leaving the oxygen to combine with surface minerals, and the water was gone forever, replaced by the thick carbon dioxide atmosphere we see today. But the upper atmosphere's faster winds hold an extraordinary possibility that tantalizes astrobiologists and planetary scientists alike. I harbor this hypothesis, or perhaps I should call it a scientific fantasy, though I do think it is plausible that there could be some kind of life living in the clouds of Venus. There are certainly energy sources available. There is sunlight penetrating the upper cloud layers, providing energy for photosynthesis or some analogous process. And there are certainly nutrients. There is carbon in the form of carbon dioxide, which dominates the atmosphere. There is hydrogen, albeit in trace amounts, and there is oxygen locked in various molecular forms. All the stuff we think of that you need to make life exists in the clouds of Venus, at least in some form. At an altitude of 35 to 40 miles, the temperature drops to a range that we would consider comfortable, perhaps 50 to 70 degrees Fahrenheit. The pressure at this altitude is similar to Earth's surface. These temperate cloud layers floating high above the hellish surface represent one of the most intriguing environments for potential life in the solar system. Earth's upper atmosphere is full of life, teeming with it, in fact. Microscopic bacteria drift on the wind at altitudes of 30 miles or more, carried aloft by updrafts from storms and volcanic eruptions. These organisms, though transported from the surface, have adapted to survive in this harsh environment of low pressure, intense ultraviolet radiation, and extreme temperature fluctuations. Some remain viable, perhaps even metabolically active, for extended periods. Could Venus be the same? Could there be microorganisms that have adapted to live permanently in the cloud layers, feeding on sulfur compounds, using sunlight for energy, reproducing and evolving in an aerial ecosystem that never touches solid ground? It is not impossible. Life on Earth colonizes every available niche, from the deepest ocean trenches to the driest deserts, from boiling hot springs to Antarctic ice. Why not the clouds of Venus? Perhaps one day we will send a probe to find out, a balloon or aircraft that can drift through the Venusian atmosphere, sampling the cloud layers, examining the chemistry, searching for the complex organic molecules and metabolic signatures that would indicate life. Such a mission would be technically challenging, but not impossible with current technology. The scientific rewards would be immense, potentially answering one of humanity's most profound questions. Are we alone? Leave Venus behind, and the next planet is Earth, our home, the third rock from the sun, a world of liquid water and abundant life. Here, too, the weather gets extreme. We are bombarded by tornadoes, violent rotating columns of air that touch down from thunderstorms and scour the landscape with winds exceeding 200 miles per hour. We endure hurricanes, massive tropical cyclones that span hundreds of miles and release energy equivalent to multiple nuclear weapons every minute. And we experience dust storms, particularly in arid regions where loose sediment can be lifted miles into the atmosphere, darkening the sky and depositing layers of dust thousands of miles from their source. On Earth, these phenomena are localized, confined to particular regions and seasons, constrained by geography and climate patterns. A hurricane strikes the coast and dissipates over land. A tornado carves a path perhaps 50 miles long before losing strength. A dust storm sweeps across the Sahara or the Gobi and eventually settles. But on the next planet out, they engulf an entire world. Over 100 years ago, when telescopes were improving but spacecraft were still the realm of science fiction, astronomers thought they had found life on Mars. They observed a dark wave that spread from the polar regions towards the equator, advancing steadily as the Martian seasons progressed. They thought it was springtime vegetation spreading across the planet, forests or grasslands greening as winter ice melted and water became available. The most enthusiastic observers, like Percival Lowell, sketched elaborate networks of canals, which they interpreted as irrigation systems built by an advanced Martian civilization to transport water from the poles to the arid equatorial regions. It was a beautiful idea, one that captured the public imagination and inspired countless works of science fiction. They were right about the season. Mars tilts at roughly 25 degrees like the Earth, so you would have summer, fall, winter, and spring like the seasons we experience. The planet's orbit is more elliptical than Earth's, so the seasons have different lengths and intensities in each hemisphere. But the basic pattern is similar. Seasons bring weather, and Mars has weather in abundance, though not the kind the early astronomers imagined. The shadow they saw spreading across the surface was actually dark rock uncovered by a violent dust storm. As the polar ice cap of frozen carbon dioxide sublimated in the spring, transitioning directly from solid to gas without passing through a liquid phase, it created powerful winds. These winds picked up the fine, reddish dust that covers much of the Martian surface and carried it across the planet. Where the dust settled, it obscured the darker volcanic bedrock beneath. Where the wind scoured it away, the dark rock was revealed. The changing patterns were not vegetation, but geology, the surface of Mars being constantly rearranged by the wind. It is all because of the way the planet tilts, that axial inclination that gives Mars its seasons, just as it gives Earth ours. The Earth takes 1 year to orbit the Sun, and in January, the northern hemisphere leans away from the Sun, and we get our winter, shorter days, lower solar angles, colder temperatures. In June, it leans inward, and we experience summer, longer days, the sun climbing high in the sky, warmth and growth. Mars follows a similar pattern, though its year is nearly twice as long, lasting 687 Earth days. This extended year means that Martian seasons are also prolonged, lasting months rather than weeks. Mars has gigantic planetary dust storms, the like of which we have never seen here on planet Earth. Events so vast and powerful that they can obscure the entire planet, rendering it a featureless sphere when viewed from orbit or through telescopes. Mars has around the same axial tilt as Earth, 25 degrees compared to our 23.5, and springtime means storms. As the southern hemisphere emerges from winter and the polar ice cap rapidly sublimates, the pressure gradients become extreme. The temperature difference between the warming southern regions and the still cold northern hemisphere drives powerful winds that can reach speeds of 60 miles per hour or more. These winds lift the fine Martian dust, particles that are smaller than those in Earth's dust storms, almost like talcum powder, easily suspended in the thin atmosphere. The Martian surface vanishes under a cloud of raging dust particles that can rise 40 miles into the sky, spreading across thousands of miles in a matter of days. These storms can persist for weeks or even months, circulating dust around the planet, enveloping everything in a ruddy haze. From the surface, the sun becomes a dim ghost, its light diffused and reddened by the suspended particulates. Temperatures at the surface paradoxically drop even as the upper atmosphere warms because the dust absorbs sunlight before it can reach the ground. Solar-powered rovers and landers face their greatest threat during these events, as the skies darken and the panels cannot generate sufficient electricity. On Earth, we get dust storms too, and they can be devastating, swallowing entire cities in walls of airborne sediment. July 5th, 2011, Arizona. The residents of Phoenix watched in awe and terror as an unstoppable 5,000-foot-high wall of dust approached from the south, a roiling mass of tan and brown that blotted out the late afternoon sun. This was a haboob. An intense dust storm formed when a collapsing thunderstorm sends its cold downdraft air spreading outward across the desert floor, lifting everything loose in its path. The wall advanced at 40 miles per hour, an implacable force of nature bearing down on the metropolitan area. Day turned to night as the leading edge smashed into Phoenix, winds gusting to 60 miles per hour, visibility dropping to zero within seconds. Thousands of tons of dust settled over the city, coating cars, infiltrating homes, clogging air filters, creating a layer of fine sediment that would take weeks to fully clean. It was a dramatic event, memorable to all who experienced it, but it was also brief, lasting perhaps 30 minutes before the worst had passed. And it was localized. 50 miles away, the sky remained clear, but the disaster stayed in one place, confined by geography and the scale of the originating thunderstorm. Mars's dust storms, by contrast, can engulf the entire planet, spreading from a local disturbance in one hemisphere to cover every square mile of the surface. On Mars, when dust gets kicked up once, it lands, but it can get kicked up again and again. The dust is reusable, perpetually recycled by the winds. There are no oceans to trap it, no vegetation to stabilize the soil, no rain to wash it out of the air. On Earth, when dust gets kicked up and then finally settles out, it is probably going to settle out into the ocean where it is gone for good, locked away in marine sediments, removed from the atmospheric cycle. But Mars has no oceans. Every particle that settles remains available for the next storm. There is nowhere on Mars where there is not ready dust and sand to add to that storm. No reservoir that permanently sequesters the material. The entire surface is essentially a dusty desert, with exposed bedrock in some regions, but unconsolidated sediment covering the majority of the planet. So these storm systems can kick up and last weeks or even months, growing from regional disturbances into planet-encircling maelstroms. The largest storms occur during southern spring and summer when Mars is nearest the Sun in its elliptical orbit and the solar heating is most intense. The combination of maximum solar input and the rapid sublimation of the southern polar cap creates the perfect conditions for atmospheric instability. Mars's incredibly dry atmosphere contributes to the storm's size and power. In the case of Earth, dust that gets up into the atmosphere is rapidly washed out by the rain and gets into the ocean or onto land where vegetation holds it. We have a hydrological cycle that continuously cleanses the atmosphere. Water evaporates from the oceans, forms clouds, precipitates as rain or snow, and carries airborne particles back to the surface. In the case of Mars, there is no comparable rain to wash the dust out. The atmosphere is far too cold and too thin for liquid water to exist. Any water ice that sublimates goes directly into the gaseous phase and remains there or redeposits as frost. So once the dust gets into the atmosphere, it just sits there until the particles, by themselves, are able to slowly settle out under the weak Martian gravity, a process that can take months. A lack of rain allows Mars's dust storms to cover the planet, turning this rust-colored world into a nearly featureless orb when viewed from space. But dust storms on Mars can be equally spectacular on a much smaller scale, localized phenomena that, while impressive, do not threaten to engulf the entire planet. NASA rovers, Spirit, Opportunity, and Curiosity have captured these extraordinary images from the surface, providing a ground-level view of Martian weather. Dust devils, whirling vortices of wind and dust, march across the plains like ghostly apparitions. These are similar to the dust devils we see in Earth's deserts, but the Martian versions are much larger and more numerous. Dust devils form when the ground heats up under the sun, creating a layer of superheated air at the surface. This hot air becomes buoyant and rises rapidly. If there is even a slight rotation in the wind, the rising air begins to spin, creating a vortex. As the spinning column of air moves across the dusty surface, it lifts particles into the air, making the otherwise invisible vortex visible as a towering column of dust. On Mars, dust devils are sucking up fine, dry iron oxide dust, the rust that gives the planet its characteristic red color. The biggest dust devils can reach 6 miles into the sky, towering structures that dwarf Earth's versions. They pump fine particles high into Mars's atmosphere, creating a haze of dust that may help control the planet's dry climate and lead to a planet-wide megastorm if conditions are right. The dust lifted by these smaller vortices increases the atmospheric dust loading, and this can act as a trigger for larger storms. The dust absorbs sunlight, heating the atmosphere and creating additional instability. This can strengthen winds, which lift more dust, which heats the atmosphere further, creating a positive feedback loop that can spiral into a global event. Even on Mars, dust storms this big are rare. Astronomers have detected just 10 planet-encircling dust storms in the last 100 years of systematic observation. They do not occur every Martian year, only when conditions are optimal, typically during the southern summer when the planet is closest to the sun. What the ancient astronomers mistook for life, for forests and fields growing green with the return of spring, was actually a megastorm, a vast atmospheric disturbance redistributing the surface material on a dead world. But even a planet-covering dust storm, impressive as it is dwarfed by the weather on the next planet out from our sun. This is the giant of our solar system, Jupiter, the king of planets. Jupiter is gigantic, a world so large that it defies easy comprehension. It is 2.5 times more massive than all the other planets in the solar system added together. If you could place Earth next to Jupiter, it would look like a marble next to a basketball. You could fit over 1,300 Earths inside Jupiter's volume. This is not merely a large planet, it is a failed star, a world that, had it accumulated perhaps 80 times more mass during its formation, would have ignited nuclear fusion in its core and become a second sun in our system. It is also home to gigantic megastorms, atmospheric disturbances that make terrestrial hurricanes look like brief eddies in a stream. Jupiter's high-speed rotation drives vast bands of counter-rotating clouds, alternating zones and belts of light and dark material that circle the planet parallel to its equator. Jupiter rotates in less than 10 hours, faster than any other planet despite its enormous size. This rapid spin creates powerful Coriolis forces that stretch weather systems into long bands, rather than allowing them to organize into circular storms, as they do on Earth. Colossal storms build along the boundaries between these zones and belts, where winds blowing in opposite directions create shear and turbulence. And this is the biggest of them all, the oldest storm in the solar system, a tempest that has raged continuously since at least the 1600s when it was first observed through early telescopes. It is 15,000 miles across, large enough that 2 or 3 Earths could fit inside it side by side, and it has persisted for over 300 years, perhaps much longer. The Great Red Spot is a storm that was raging when Isaac Newton was formulating his laws of motion, when the American colonies were being established, when the Industrial Revolution transformed human civilization. It has outlasted empires and ages, a testament to the stability and power of Jovian weather systems. Around the edges of the Great Red Spot, turbulent winds rage at over 300 miles per hour, velocities that would tear apart any structure humans could build. The storm rotates counterclockwise, taking about 6 Earth days to complete one rotation. The winds at the periphery are fastest, while the center, like the eye of a terrestrial hurricane, is relatively calm. The storm's distinctive red color has been the subject of much scientific debate. Some researchers believe it comes from complex organic molecules created by solar ultraviolet light acting on simpler compounds in Jupiter's atmosphere. Others suggest that the color is due to phosphorus or sulfur compounds dredged up from deeper layers. The color has varied over time, sometimes appearing brick red, other times fading to a paler salmon hue, suggesting that the chemistry or structure of the storm changes even as the storm itself persists. The Great Red Spot is a giant vortex, meaning that in the case of the red spot, it has a high pressure center with winds that swirl around the outer edge. So, in that sense, the Great Red Spot is a little bit like a hurricane, at least in its general structure and rotation. But this is a hurricane with a difference, a storm that operates by rules unlike those that govern terrestrial weather. On Earth, hurricanes feed off heat from the ocean, drawing energy from warm tropical waters. Evaporation from the sea surface rises into the storm, condenses into clouds and rain, and releases latent heat that powers the circulation. When hurricanes hit land, they are cut off from their energy source. The winds over land create friction that slows the rotation. So, on average, terrestrial hurricanes last only about a week, perhaps two if conditions are exceptionally favorable. Then they dissipate, their energy spent, their structure degraded. Jupiter does not have land. Jupiter is a completely gaseous planet, or more precisely, it has no solid surface accessible from above. There is no boundary where the storm can lose its energy to friction against a solid substrate. The friction there, in the atmosphere itself, is very weak. Gas molecules slide past one another with minimal resistance compared to the drag that a hurricane experiences when its winds encounter buildings, trees, and terrain. And so, a vortex like the Great Red Spot can last indefinitely. There is nothing to slow it down, nothing to disrupt the organized circulation. It just keeps going, decade after decade, century after century. All the red spot needs is a power source, energy to replace what is slowly lost to the weak friction and turbulence at its boundaries. On Earth, ultimately, that energy is heat from the sun, which warms the oceans and creates the temperature and pressure gradients that drive our weather. But Jupiter is 5 times farther from the sun than we are, orbiting at a distance of nearly 500 million miles. At that distance, the sun appears only a fifth as large in Jupiter's sky as it does from Earth, and the solar energy received per square meter is only 4% of what Earth receives. Heat from the sun is not enough to drive the red spot or the powerful jet streams that circle the planet. Instead, Jupiter has an internal power source, energy left over from its formation and from ongoing gravitational processes deep within the planet. Its own immense gravity is the key. In 1995, NASA launched the Galileo spacecraft, which carried a probe designed to plunge straight toward the giant planet's heart. It was a suicide mission for the probe, a one-way trip into conditions no spacecraft had ever been designed to withstand. On December 7th, 1995, the probe separated from the orbiter and began its final descent. It plunged into Jupiter's upper atmosphere at over 106,000 miles per hour, faster than any human-made object had ever entered a planetary atmosphere. Friction with the thickening gases heated the probe's heat shield to over 30,000 degrees Fahrenheit, hotter than the surface of the sun, as it screamed down through the cloud tops. As it fell, the planet's crushing gravity ratcheted up the pressure, 10 times what we feel on Earth, then 15, then 20. The probe deployed its parachute and began transmitting data, radioing back information about temperature, pressure, chemical composition, and wind speed. The winds gusted to over 400 miles per hour, higher than mission scientists had anticipated, battering the descending probe. The probe gave out just 100 miles in, barely scratching the surface of this gas giant. It was crushed by pressure exceeding 20 times Earth's sea level and fried by the incredible heat that the pressure generated, temperatures approaching 300 degrees Fahrenheit. The signal ceased, and the probe was destroyed, compressed and incinerated in the depths. Had the probe made it deeper, descending hundreds or thousands of miles into the interior, it would have encountered ever more extreme conditions. Eventually, thousands of miles down, it would have reached a vast, silvery ocean, not water, but something far stranger. Intense pressures here, in excess of 2 million times Earth's surface pressure, turn hydrogen gas into a churning metallic liquid superheated to over 40,000 degrees Fahrenheit. This is a state of matter that does not exist naturally on Earth. Hydrogen compressed so intensely that its electrons are stripped free and the substance behaves like a molten metal, capable of conducting electricity and generating magnetic fields. This ocean of metallic hydrogen, thousands of miles deep, surrounds Jupiter's small rocky core, if indeed a discrete core exists at all. Jupiter's interior pumps out about twice as much energy as the surface receives from the sun, radiating infrared heat into space from its own internal reserves. This is Jupiter's power source, the engine that drives its massive megastorms. When Jupiter formed 4.5 billion years ago, it coalesced from the solar nebula, accumulating gas and dust through gravitational attraction. As the material fell inward, gravitational potential energy was converted to heat, and the proto-Jupiter became hot. Over billions of years, the planet has been slowly cooling, radiating that primordial heat into space. Additionally, helium droplets rain down through the metallic hydrogen ocean, releasing gravitational energy as they sink toward the core. This ongoing process of differentiation continues to generate heat. All of the convection, all of the heat that reaches Jupiter's cloud tops comes from the hot, dense interior of the planet itself. Heat flows outward from the depths, creating powerful convection currents that rise through thousands of miles of atmosphere. So the bands of clouds that you see, those alternating light and dark stripes, the zones and belts that are even counter-rotating, going in different directions, those are all driven by the internal heat of Jupiter itself. The zones are regions where gas is rising, carrying heat upward from below. As it rises, it expands and cools, and ammonia condenses into white clouds at high altitude. The belts are regions where gas is sinking back down, having radiated its heat to space. The descending gas is warmer at a given altitude, so the clouds form deeper, revealing the darker chemistry beneath. Jupiter's internal heat drives its violent megastorms, but the giant planet may hold clues to an even deeper mystery, one that extends beyond planetary science into the realm of biology and the search for life beyond Earth. Could life exist on other worlds, not just in the past, not just as fossilized bacteria in Martian rocks, but right now, thriving in alien environments we have barely begun to explore? NASA's Cassini probe studied Jupiter as it flew past en route to Saturn in the year 2000, using the giant planet's gravity to accelerate and redirect its trajectory. During this flyby, it made an extraordinary discovery while photographing Jupiter's turbulent atmosphere. Strange white clouds appeared just north of the Great Red Spot, bright patches that stood out against the surrounding rust and tan bands. These were clouds, just like the clouds on Earth, not ammonia ice or methane haze, but droplets of liquid water, H2O, the universal solvent, the medium in which all terrestrial life exists. Could Jupiter have the ingredients for life? The question of life on the giant planets is an interesting one that has fascinated astrobiologists since the 1970s, when Carl Sagan and others first speculated about the possibility. You have many of the ingredients for life on Jupiter. You have sunlight coming in, providing energy that could potentially be harvested through photosynthesis or some analogous chemical process. There is liquid water, at least in the form of cloud droplets suspended in the atmosphere at altitudes where the temperature and pressure are clement. There is carbon, the backbone of all organic chemistry, present in methane and other hydrocarbons. There is nitrogen in the form of ammonia, hydrogen in abundance, oxygen bound in water, and other molecules. All the stuff we think of that you need to make life exists in the clouds of Jupiter, available, mixing, bathed in energy. On the other hand, if life can easily exist in clouds, you might expect that bacteria and algae would populate the clouds on Earth, and the clouds would be green, visibly colored by chlorophyll or other pigments. We do not see that on Earth. Our clouds remain white because they are composed of water droplets or ice crystals, not biological material. We do see microbes at many altitudes throughout Earth's atmosphere, carried aloft by winds and storms, but they seem to largely be blown off of the surface rather than living permanently in the sky. Atmospheric microbes on Earth are transients, surviving in a dormant state until they settle back to the surface. They did not originate in the clouds. They are emigrants from terrestrial ecosystems. It is likely that life on Earth began on a solid surface, perhaps in tidal pools where organic molecules could concentrate, or near hydrothermal vents on the seafloor where chemical energy was abundant. Having a solid surface provides stability, a place where complex molecules can accumulate, where cells can anchor and form colonies, where nutrients can concentrate. But could life evolve without one? Could there be organisms that live their entire existence floating in the atmosphere, never touching ground because there is no ground to touch? There is no surface on Jupiter, at least not one that resembles the solid crust of a terrestrial planet. Descend far enough, and the atmosphere simply becomes denser and hotter, transitioning gradually from gas to liquid, to perhaps a slush of exotic ices, and finally to that metallic hydrogen ocean. But there is no place to stand, no seafloor, no land, and that makes it difficult for organisms to have a constant source of water and nutrients. So if you imagine yourself being a little bacterium inside a cloud droplet, you are going to be in deep trouble when that cloud droplet evaporates. On Jupiter, clouds form at specific altitudes where the temperature allows water vapor to condense. But the atmosphere is dynamic, with powerful updrafts and downdrafts. A cloud droplet might descend into warmer, drier layers and evaporate, potentially killing any organism inside. Or it might rise into colder layers and freeze solid. Surviving in such an environment would require adaptations that no terrestrial organism possesses: the ability to enter dormancy rapidly, to withstand desiccation and freezing, to somehow navigate vertically to remain in the habitable zone. Whether life exists in Jupiter's clouds or not remains an open question, one that may not be answered for decades. Gas giants like Jupiter and its neighbor Saturn have all the right ingredients for life: water, heat, and one other vital element that might provide the spark needed to transform chemistry into biology. A spark, literally. Lightning on an unimaginable scale crackles through these alien skies. These haunting images are from NASA's Cassini probe, the spacecraft that has spent over a decade exploring one of the solar system's most awe-inspiring planets, Saturn. Its mission to explore not just the ringed giant, but its vast retinue of moons, some of which may harbor subsurface oceans and the potential for life. The probe reveals Saturn's rings, moons, and the planet itself in near perfect detail, images of such clarity and beauty that they seem almost unreal. Chaotic bands of cloud race around Saturn at more than 1,000 miles per hour, driven by the same internal heat source that powers Jupiter's weather. The clouds are composed of ammonia ice crystals in the upper layers, with water ice and perhaps ammonium hydrosulfide at deeper levels. The colors are more muted than Jupiter's, giving Saturn a serene butterscotch appearance. But this apparent calm is deceptive. Finding storms here was no surprise. It is a planet of storms, a world where atmospheric instability is the norm. But this was astonishing. Cassini captured images of a bolt of lightning, a gigantic thunderstorm on an alien world, discharge of electricity on a scale that dwarfed anything we see on Earth. Lightning creates some of the most spectacular weather on Earth, dramatic displays of nature's power that have inspired awe and fear since humans first looked up at a stormy sky. Electrical tension builds between the top and bottom of a vast 55,000-foot-high storm cloud, a towering cumulonimbus, a maelstrom of water vapor, rain, and ice. Inside this cloud, powerful updrafts and downdrafts separate charges. Tiny ice crystals, light and positively charged, are driven upward past hailstones, heavy and negatively charged, falling downward. As they rub past each other, collide, and separate, it builds up a charge, creating an electric field of immense strength. The top of the cloud becomes positively charged, the bottom negatively charged, and the ground below acquires a positive charge by induction. When the strain gets too great, when the electric field exceeds the breakdown voltage of air, you get an electric spark that we call lightning. On Earth, the average lightning storm stretches 15 miles. A single cumulonimbus cell or cluster of cells producing dozens or hundreds of strokes. But on Saturn, they can reach around the whole planet, not as single continuous bolts, but as storm systems so vast that they wrap around the globe. There are examples of lightning storms on Jupiter and Saturn where the anvil cloud, in other words, the big cloud at the top of the storm, the flattened spreading region where the updraft hits the tropopause and spreads horizontally, starts small, perhaps a few hundred miles across, and grows to be 20,000 kilometers long. That is the size of the Earth. On Saturn, we registered one lightning storm that was 10,000 times greater in energy output than any lightning storm found on planet Earth. Discharges so powerful that they were detectable from Cassini's instruments hundreds of thousands of miles away. Lightning is hotter than the surface of the sun, a channel of plasma reaching 50,000 degrees Fahrenheit in the fraction of a second that the current flows. The atmosphere literally explodes, heated so rapidly that it expands faster than sound, creating a shock wave. That shock wave is the sound we call thunder on Earth, the acoustic signature of the bolt, traveling outward at the speed of sound. It is the sound of the sky being torn apart and then healing, of energy released on a scale that humans can barely produce, even with our most powerful technology. But lightning is more than destruction. It is, paradoxically, one of the processes that enabled life to flourish on our planet. Lightning seems scary and destructive, but actually it is very productive for life on Earth, a vital component of the nitrogen cycle that makes this element available to living organisms. And the reason why is because of its influence on atmospheric chemistry, its ability to break apart the most stable molecules and forge new compounds that would not otherwise form in Earth's clement conditions. Every bolt literally burns the air, creating a tiny region of extreme temperature and pressure where chemical reactions that normally require industrial conditions occur naturally. When you have a lightning discharge, you get this very high temperature, very energetic plasma, and that breaks up the nitrogen molecules in the atmosphere. Nitrogen gas, N2, is extraordinarily stable. The triple bond between the two nitrogen atoms is one of the strongest bonds in chemistry. At normal temperatures, temperatures and pressures, nitrogen is inert, unreactive, essentially invisible to most chemical processes, despite making up 78% of our atmosphere. But lightning, with its extreme heat, rips these molecules apart, freeing up those nitrogen atoms to enter into other kinds of molecules, to combine with oxygen and hydrogen, forming nitrogen oxides and eventually nitrates. And those nitrates formed by lightning allow nitrogen to go into the soil as basically fertilizer, entering into plants through their roots, being incorporated into amino acids and proteins, entering into the life cycle as an essential nutrient. So it is the lightning that frees up nitrogen atoms in the service of life on Earth. Without this natural fertilization process, life on land would be far more limited. Some organisms, certain bacteria, have evolved the ability to fix nitrogen directly from the atmosphere, but lightning provides a non-biological pathway that has been operating since Earth first had both an atmosphere and liquid water. Earth experiences 8 million lightning bolts every day, a constant bombardment that deposits nitrogen compounds into soil and water, helping life evolve and colonize the planet. Over billions of years, this process has contributed significantly to the nitrogen available to the biosphere. But for Saturn, lightning alone may not be enough to spark life. The absence of a solid surface or a liquid ocean below the clouds makes it difficult to imagine how even the most robust ecosystem could establish itself. One place in our solar system may solve that problem, a world that combines an atmosphere, organic chemistry, lightning, and most remarkably, stable bodies of liquid on its surface. Saturn's moon Titan. It has an atmosphere thicker than Earth's, composed mostly of nitrogen with significant methane. It has lakes, not of water, but of liquid methane and ethane, hydrocarbons that remain liquid at the frigid temperatures of the outer solar system. And it has its own bizarre brand of megastorms, weather systems driven by the slow evaporation and condensation of methane, creating a hydrological cycle remarkably similar to our own, despite occurring at temperatures nearly 300 degrees below zero. Saturn is almost 900 million miles from the Sun, orbiting in the cold outer reaches where sunlight is faint and seasons are measured not in months but in years. This far out, orbiting the Sun takes time. Saturn's year is nearly 30 Earth years long, and its pronounced axial tilt gives it seasons much like our own, though extended over decades rather than mere months. Right now, as of the second decade of the 21st century, it is spring in Saturn's northern hemisphere, and things are heating up, relatively speaking. Now we are moving into the summer cycle of Saturn, the long, slow warming that follows the spring equinox. So the atmosphere is slightly heating up, absorbing more sunlight as the northern hemisphere tilts toward the sun. Even as distant as Saturn is from the sun, even with solar energy reduced to 1% of what Earth receives, we have got a little more energy input, and we are seeing the most spectacular storms we have ever observed on Saturn. Convective outbursts that form brilliant white spots visible even through amateur telescopes. After years of frozen silence, Saturn is coming alive. Scientists have waited nearly 15 years since the Cassini probe arrived in 2004 for the sun to light up Saturn's North Pole and reveal extraordinary details about one of the strangest megastorms in the solar system. Saturn's unique hexagon storm, a hexagonal pattern traced by clouds circling the North Pole with geometric precision. How can that be? In Mother Nature, we have jagged objects, fractals, spirals, and organic forms that repeat on different scales. We do not have geometric figures arranged precisely, especially at a gigantic planetary scale where you would expect chaos to dominate. The hexagon is nearly 15,000 miles across, wider than Earth, a shape so regular it looks artificial. However, there are some theories that attempt to explain this bizarre phenomenon. If I take a bucket of water or a bathtub and simply vibrate it at certain frequencies, I get waves, traveling waves that propagate across the surface. But there is another kind of wave, less familiar but equally important in fluid dynamics. You have traveling waves, but then you have stationary waves, standing waves that do not propagate but oscillate in place. Inside a bucket of water, you can get resonances, natural frequencies at which the container and the fluid prefer to vibrate. Water pulsates up and down in one pattern, or it can pulsate in a circle, forming concentric rings. And you can also get them to pulsate in more complex modes, forming regular patterns with specific numbers of nodes and antinodes. These are called stationary waves or standing waves. And we think that this mysterious hexagonal pattern on Saturn is a hexagonal standing wave, a resonance in the jet stream that circles the pole. The jet stream at Saturn's North Pole travels at roughly 200 miles per hour, and for reasons still not entirely understood, it forms six discrete corners rather than flowing in a smooth circle. Laboratory experiments have reproduced similar polygonal patterns by rotating fluids at different speeds in concentric cylinders, demonstrating that under the right conditions, fluid dynamics naturally produces these geometric forms. The megastorm at Saturn's North Pole is a wind that travels at hurricane speed, cornering sharply 6 times as it races around the planet, each straight edge of the hexagon measuring some 9,000 miles. The central clearing, the region inside the hexagon, is so big you could fit 4 Earths inside, a vast polar vortex analogous to the circumpolar winds on Earth, but far larger and apparently far more stable. This feature has persisted for at least the several decades we have been able to observe it, and possibly for far longer, perhaps centuries or millennia. What lies beneath its surface is a mystery. Does the hexagon extend deep into the atmosphere, penetrating hundreds of miles into the interior? Or is it a shallow feature confined to the cloud tops? We do not yet know. As Saturn warms from spring to summer, another world comes alive too. Not the planet itself, but one of its enigmatic moons. One of Saturn's moons, Titan, is warming up as well, its northern hemisphere emerging from 15 years of winter darkness. And with the warmth come the storms, atmospheric disturbances that astronomers have been eagerly waiting to observe. One of the most interesting moons in our solar system is Titan, the only moon with a substantial atmosphere, a world straight out of science fiction. It is an object with yellow skies, a thick nitrogen atmosphere tinted orange by organic haze, and methane clouds that drift and occasionally precipitate. That is truly remarkable, a moon with weather, with seasons, with precipitation cycles, a world that in some ways resembles a frozen version of early Earth. NASA's Cassini probe, along with its companion Huygens lander, built by the European Space Agency, has revealed Titan in unprecedented detail over more than a decade of observation. A thick, dense atmosphere, 1.5 times the surface pressure of Earth despite Titan's smaller size, composed of 98% nitrogen and 2% methane, with traces of other hydrocarbons. Vast mountain ranges rising several thousand feet, carved by processes we do not fully understand. Lakes of liquid methane and ethane concentrated near the poles, bodies of liquid covering thousands of square miles, shorelines and bays and inlets reminiscent of terrestrial geography. And this an arrow-shaped band of white methane clouds moving over its surface, photographed by Cassini's infrared instruments that can penetrate the thick atmospheric haze. When the clouds drifted over a dusty, open plain, seen here as a dark patch in infrared images, the dark patch of ground beneath the clouds grew larger, spreading outward from where the clouds had passed. Scientists believe liquid methane drenched the surface, darkening it just as water darkens terrestrial soil when it rains. It was a spring rainstorm, Titan style, the first precipitation event directly observed on another world. Rain on Titan, if it exists, and the evidence now strongly suggests it does, would be very different from rain on planet Earth. First of all, the gravitational field is weak, only 14% of Earth's surface gravity. So you would actually see raindrops falling very slowly toward you, drifting down like snowflakes on Earth. It would take perhaps a minute for a drop to fall from cloud base to the surface, compared to just seconds on Earth. Also, the size of these droplets could be much larger, possibly half an inch or more in diameter, because the surface tension of liquid methane is lower than that of water, and the thick atmosphere provides buoyancy. But do not get caught in a rainstorm on Titan. Those droplets are awfully cold, minus 290 degrees Fahrenheit, cold enough to freeze any terrestrial organism instantly. Methane rain would feel like being sprayed with liquid natural gas, which, in essence, it is. And the raindrops are not water, but hydrocarbons, substances that on Earth we burn as fuel. Titan's methane monsoon sweeps across the moon during seasonal transitions when the sun crosses the equator and atmospheric circulation patterns shift. Weak gravity creates ultra-cold hazelnut-sized raindrops that fall gently from the orange sky, spattering on the frozen water ice bedrock and pooling in depressions, forming rivers that flow to the polar lakes. An alien world with truly alien weather, yet one that operates on principles familiar to terrestrial meteorologists. These slow drops, falling over millions of years, have carved valleys and lakes much like water has carved Earth's landscape. Titan has river channels, dendritic drainage networks, alluvial fans, features that on Earth are produced by flowing liquid. The channels imaged by Cassini and by the Huygens lander, which successfully touched down on Titan's surface in 2005, show rounded pebbles of water ice, apparently smoothed by the action of flowing methane. It is a slow-motion megastorm planet, a world where the methane cycle operates much as the water cycle does on Earth, but at a languid pace, dictated by cold temperatures and weak solar heating. But fly even farther out through the solar system, past Titan and Saturn, past the orbit of Uranus, and you find storms that are altogether faster, more violent, driven by forces we are only beginning to understand. This is super-chilled Neptune, the eighth planet, orbiting nearly 3 billion miles from the Sun. The temperature never gets above 300 degrees below zero. Neptune is one of these giant planets, an ice giant smaller than Jupiter and Saturn, but still much larger than Earth, 17 times our mass and about 4 times our diameter. It has a very thick atmosphere of hydrogen, helium, and methane, which gives it its distinctive deep blue color. It is about 2 billion miles out from the Sun, so far that sunlight takes more than 4 hours to reach it. So you really might expect, since it is that far from the Sun, it would be very cold and not have very much weather, a dormant world with a placid atmosphere. But in fact, Neptune is very dynamic. It has got tremendous weather patterns, storms that rival Jupiter's in speed, if not in longevity. Despite its incredible distance from Earth, astronauts can get close to Neptune's turbulent atmosphere with a little help from advanced technology. With a little help from this, the Keck Observatory, two massive telescopes 14,000 feet up on the summit of Mauna Kea in Hawaii. The observatory sits above much of Earth's atmospheric water vapor and pollution, in thin air where the seeing conditions are among the best on the planet. The telescopes are so powerful they could see a candle on the moon, or resolve details on planetary surfaces that were once visible only to spacecraft. Neptune at first appears featureless when viewed through smaller telescopes, just a tiny blue disk. But a closer look through Keck's 10-meter mirrors reveals white, high-altitude clouds in the upper atmosphere, brilliant streaks of methane ice crystals condensing at the coldest levels, where the temperature drops to nearly 400 degrees below zero. It is a perfect opportunity to track wind speed, to measure how fast these clouds are racing around the planet. Measuring the time and distance the clouds take between 2 points allows scientists to clock their speed with precision. The Keck telescope swings towards Neptune over multiple nights. A series of shots track the white clouds as they move around the planet, their positions changing relative to the background stars and to Neptune's rotation. So here we can take several photographs that show the positions of clouds apparently changing. You can measure the position at one moment to be at a certain longitude, and at another time, a few hours later, to be at a different longitude. Now, most of that change in position is due to the rotation of the planet as a whole, Neptune's 16-hour day spinning the globe beneath the clouds. However, if you know the rotation rate of the interior, determined from radio emissions generated by Neptune's magnetic field, and subtract that out, that gives you the motion of the clouds relative to the planet. That tells you the wind speed, the velocity of the atmosphere relative to the solid body rotation. The results are shocking. We are seeing wind speeds on Neptune of many hundreds of miles per hour, up to 1,200 or even 1,260 miles per hour for the very fastest clouds, velocities that exceed the speed of sound in Neptune's cold atmosphere. That is really phenomenal, faster than any wind measured on any other planet in the solar system. Neptune has the fastest winds in the solar system, and this presents a profound mystery. So what is driving this? You need energy to make weather, to drive winds, to power storms. Where is that energy coming from? And it turns out it is coming from Neptune itself, from the planet's interior, not from the sun. It does receive sunlight, but Neptune actually radiates away more energy, a lot more energy, 2.6 times as much, than it gets from the sun, which means the interior is very hot. Probably it means there is radioactive material in there, decay of uranium, thorium, and potassium generating heat over billions of years. There is leftover heat from when Neptune formed 4.5 billion years ago, gravitational potential energy converted to thermal energy during the planet's accretion, heat that is very slowly leaking out. And it is that internal heat that is heating up the air and driving all of the circulation and all of this crazy weather that Neptune has, winds that howl through the frigid atmosphere with unimaginable fury. Neptune's storms hit hard with violence that makes terrestrial hurricanes look gentle. But the search for truly extreme weather takes us out of the solar system altogether into uncharted territory beyond the realm of planets orbiting our sun. Out here, orbiting distant stars, there are storms that make even Neptune's 1,200-mile-per-hour winds look like a breeze. Katrina was just a sneeze compared to the winds we have on some of these exoplanets, worlds so different from anything in our solar system that they challenge our understanding of planetary physics. The search for megastorms leads to alien worlds whose violence defies imagination, planets discovered only in the last few decades, orbiting stars dozens or hundreds of light years away. Space is full of stars, and as we have recently discovered, full of planets, worlds where violence and chaos reign, where the conditions are so extreme that they redefine our concept of what a planet can be. Astronomers scour the skies for new worlds with ever more sophisticated instruments and techniques. And the king of the planet hunters is Professor Jeff Marcy, an astronomer at the University of California, Berkeley, who has discovered or co-discovered more exoplanets than any other scientist. He scans the night sky with powerful spectrographs, seeking the tiny wobbles in starlight that betray the presence of orbiting worlds, seeking new planets around distant stars. Marcy's team has instruments so sensitive they can even predict the weather on these distant planets by analyzing the starlight filtered through their atmospheres. This is Osiris, officially designated HD 209458b, 150 light years from Earth, a planet from hell with matching weather. Earth is 93 million miles from the Sun. It orbits the Sun in 1 year, 365 days of warmth and cold, summer and winter. But Osiris is just 4 million miles from its star, orbiting 23 times closer than Earth does to the Sun. Its year races by in just 3.5 days, a dizzying pace where the seasons, if they could be said to exist, would last mere hours.